Hi everyone, thank you for attending. Welcome to Jailbreak Do It Yourself. My name is Max, I'm here with Alex and Vlad, and we are Fried Apple team. A few words about us. We are a security research team, mostly focused on software and hardware exploitation. We made a various jailbreak for iOS, tvOS, even the watchOS, and we are contributing to a jailbreak community. So before jumping to a jailbreak, let's make a quick overview of iOS security. iOS security starts from a secure boot chain, when each element in a boot chain got properly checked to be signed by Apple and reject the boot chain if it's not. The next thing after iOS is loaded is a mandatory code signing. So all code that's running on iOS should be signed by Apple or should be signed by a trusted party. The sandbox, which is limiting application access to a file system to some critical APIs. And Apple made a really good work on exploit mitigations, like heap and stack canaries, like isolar, like deb, and hardening Safari JIT in the iOS 10 release. Next, the data protection, which secure user partition based on a passcode or the Touch ID. Secure enclave processor, which uses it as a secure crypto operations as a provider for Apple Pay. And one more thing is kernel patch protector. It's a new mitigation debuted in iOS 9. It's a special monitor that can continuously check for a kernel integrity. So what is a jailbreak? So basically, jailbreak is a process of hacking your device. As a user, you cannot get a full access to a file system. You cannot run something like SSH daemon on your phone and tunnel to your phone. So in any case, to get a full access and install any third-party applications and utils, you need to jailbreak or hack a device. Nowadays, the exploit chain is required. And it could take like up to from 3 to 7 or 8 exploits in a chain to get a fully untethered jailbreak. As we talk about the untethered, there are two types of jailbreaks, tethered and untethered. The main difference is in a tethered jailbreak, it effectively will be invalidated after the device got rebooted. So this means after the device rebooted, you need to run exploit again, which do all the kernel patches. In the case of untethered, jailbreak will be running automatically on device boot. So the next thing is, what are the possible initial attack vector? How to install the payload which contains a jailbreak on a device. The most easy and the most popular way is making application archive, install it on device, which will basically trigger the exploit code. The USB payload is pretty good attack. We can exploit USB commands itself or use USB as one of the stages when the file with exploit got copied to a device and will be used by the next stage. Of course, the WebKit, SMS, and baseband, like mobile Safari, like any libraries that do image rendering in iMessages, and of course Wi-Fi and LTE baseband. That's a really good target for remote jailbreaks. So let's assume you want to make a jailbreak and you have 0 days. Well, in this case, the process will be not that hard. You just need to write exploit chain, which will patch out all the security restrictions in the system. Optionally install persistent binary and SSH or any other remote shell. But as we know, the 0 days are pretty expensive. So what if you don't have 0 days? Jailbreak is still doable. As there are so many public POCs and write-ups on iOS bugs, like Google Project Zero do a really great things by publishing POCs, and the Pango team, Pango blog is really good. They describe a lot of iOS exploitation. The main difference that all those public sources, they do not contain the information how to make a full jailbreak, how to disable iOS restrictions, how to bypass the kernel patch protection, which is really, really critical if you want to make any kernel patch. So that's the things we want to solve in our talk. We want to show a step-by-step guide how to make a jailbreak at home. So I will start with arbitrary code execution strategies, or how to bypass initial code signing checks. So first of all, there's a well-known techniques, return-oriented programming, which is well documented, and I will not focus on it too much. The next thing is binary with match bug. So main idea is to exploit dynamic linker and hide executable segment by overlapping it with non-executable. So when kernel see binary, it see, okay, so there's no executable segment, so I should not check a code sign here. Next thing is JavaScript core. JavaScript core is very interesting because it contains a special memory region that could be readable, writable, and executable in the same time. So if we can exploit it and leak the JIT region address, we can overwrite it with a shell code and basically, yeah, run and sign code. There is, of course, the poor manner way to run and sign code or sign it code. Now Apple allow any Apple ID use it as a code signature, but this signature will be invalidated in a week. The next thing is a sandbox. So a way to attack sandbox is time of check, time of use bugs in combination with the symlinks. So for example, we can use a race condition in services, in mobile installation services, that will verify a file, and before it got copied to a file system, we can replace a file on a disk. Or use a symlinks attack, for example, changing the path in a playlist to something we control, which leads when the application will be installed by mobile installation services, it will install our file to an interesting path that's followed by a symlink. XPC. XPC is a really good mechanism to communicate between the processes. And if we found the XPC bug, we can basically send action commands to other processes. Hey, please copy this file from folder A to folder B, or chmod this file to be executable, and so on. XPC is pretty powerful. And if we get a kernel write primitive, the sandbox bypass is really trivial. We can disable it locally for our process by updating the proc structure in the kernel memory, or even globally by patching a kernel. I will show it a little bit later. The next thing is, what are the strategies to escalate privileges and why we really need it? So in IIS, most of the critical system APIs, they require you to be root for usage. Like task for Pete, hostget special port, even remount can be used without being root. So the general idea is to find a service that's running as root and find what libraries it is loading. And base it on code sign bypass, or base it on something like jump to a rope chain before code sign in the library will be triggered. We can run a code with a system, with the root privileges. Again, the kernel page, if we get a kernel write, it's pretty easy to update the kernel memory, the correct structure, and write root permission there. I will show it a little bit later. The next thing is KSLR. So Apple introduced address space layout randomization starting with iOS 4.3. And they added KSLR to a kernel starting from iOS 6. So the idea behind the mitigation is that kernel address got randomized each time device is boot. And for attacker, before attacking or patching a kernel, he needs to know where it is located. A pretty popular way to bypass KSLR is information leak. So the idea is that we can use something like structure size mismatching, and some of the kernel memory will be copied to a user mode. And usually one pointer is enough to understand the kernel base address. Markdown and Tarjuman, they made a really good write-up on there on early random weaknesses, which allow to even the brute force the KSLR slide, as well as work by Esther. I can say even in iOS 10, it's possible to brute force KSLR. All we need is a kernel read primitive and continuously check for a kernel header in a memory. So for example, Ian Beer was using this technique in the Mac Portal jailbreak. The next thing is DEP, data execution prevention. Again, JavaScript core is a really good target, as it contains the JIT region, which is writable, readable, executable. If we can leak this address, overwrite it with a shell code, we bypass a DEP. It could be attacked from a user land. For example, if we found a bug in a way how the pages got locked. For example, we can map a writable page, overwrite it with a shell code, switch it to be executable, and if we found any way to lock a page, it will be never page out, and code sign handler will be not triggered on this page. Basically, we can run shellcode in a user mode. So the last attack we know was in IS 9.3 using mlock or IOService. Of course, we can do a kernel page. So with a kernel page, we can override VM map enter, VM map protect, and with this easily allocate readable, writable, executable pages in userland. If there are no other options, ROP is still an option, return array and program away. So the next problem is there are so many kernel builds, there are so many devices, and making like a table with all the offsets is not a trivial task. So we need to solve a problem how to find the offsets for patch just dynamically in a memory. So for these purposes, patch finders, I use it. There are a few ways to make a patch finder, like a static or a dynamic. Static patch finder is based on string or byte references. Then you find a xref to it and make additional instruction analysis for find a function start or interesting variable or so. Again, it's not that good as it based on a pattern matching. Other ways to make it is a dynamic patch finder. Idea behind it, there is a structs in a kernel that never really change it. For example, syscall, CTL, match syscalls. Those tables just grow, so they did not really change anything in the middle. So as soon as you can leak the address of syscall table, you automatically resolve more than 500 functions in a kernel. In combination with instruction emulations, instead of byte patterns, it will be like a pretty powerful tool. So let's assume we have a patch finder. What we should patch in a kernel to get a jailbreak? We need to make the page to easily become a root. We made the page to easily export kernel task port, which is a task for PID. We need to disable code silence formats, sandbox, and finally remount system partition as readable writable. I will focus on each of these patches a little bit detailed. So escalating privileges. As I say, most of the APIs, critical system APIs, they require root to work. Task for PID, mount, host get special ports, and so on. So in a case to use these APIs, we need to escalate privileges. A pretty popular way is if we bypass a kernel page protector to patch a kernel directly, which is a setReid syscall, which is there is a check that comparing real UID with effective UID. There's like a set of these checks. So all we need to do to find it in a setReid function and basically patch to skip this condition at all. This is how it looks like. So it's a setReid function. There is like a set of checks that comparing real UID with effective UID. So all we need to patch is to make sure there is that the code will not jump in this condition. The next thing is a kernel task. So the task port is a type of MAC port type, and it has a pointer to the struct task in a kernel memory. So if we have a send write to this port, we can control over virtual memory of any process. We can control of the threads and so on. So in the case of kernel, if we get a kernel task port, we can control the kernel memory. So it's like readable, writable primitive. We can allocate memory in a kernel, and so on. There's a lot of utils that require kernel task port to be exported. Most of these utils are for working with a kernel. So what are the possible ways to export the kernel task port? First of all, there is a function called task for PID, which is basically a return the task port for interesting PID. And of course, there are checks to make sure we cannot export the kernel task. So we can patch this one. We can even re-implement the task for PID in ROP. The basic idea to implement only the functionality we need and skipping the checks. It may be not that trivial. And if there are no other ways, we can always find the kernel task port in a memory and export it. This is how the task for PID page may look like. So Apple hard-coded check for PID0, which is a kernel PID, to make sure that any process cannot export the kernel task. So what we need to do, we need to null out this check. But it's not that easy. as there are additional checks in a case if you are running not as root. So if you are not root, we need to patch out task for PID POSIX checks. Again, we need to patch out PID 0 check and patch out chaos create issue. So these two additional checks which are checking for, do we have a permissions to export this task port, and are we running as root, again, to get that task port for interesting process. Next thing is Apple mobile file integrity. So it's like a main module that is checking for that code is signed, that it is properly signed by a certificate, that the entitlements match the hashes that are in a code sign. It grants access to other processes' task ports and have restrictions on a map and so on. So it's like a pretty powerful kernel extension. And for sure, for making a full jailbreak, we need to disable Amphi. A few ways of doing that. There is a really interesting boot argument called Amphi get out of my way. It doesn't exist on release kernels and release device, but Amphi still respects this boot argument. So this means if you find the variable that reads the value of Amphi get out of my way and patch it directly in kernel, you'll get Amphi get out of my way functionality. The same thing, we need to enable the debug mode. The debug mode will disable a lot of security features like a code sign and like something in remount. Other way, we can patch only interesting policies directly in Amphi text. This is how it looks like. So as I say, Amphi init respect Amphi and Amphi get out of my way boot arguments. If they exist, it reads the corresponding value of these boot arguments and set the variables. So we can directly patch these variables to get Amphi get out of my way functionality. The next thing is Amphi policy patches. So Amphi kernel extension have a pointer to MAC policy configuration, which is basically a structure, and one of the fields contain MAC policy operations. And these operations are basically pointers to MAC hooks, Amphi MAC hooks. So what we can do, we can look for Apple mobile file integrity string, find the reference to it, and a few instructions on top, we will see a reference to MAC policy operations, which is like an array like this. And if we null out all of these pointers, no Amphi hooks will be triggered. We can, well, there is a list of Amphi policies to patch, and we can patch only the interesting one. So as we see here, there is mmap checks like for team ID, there is mprotect check, there is even file check library validation, or vnode check signature. So there's a lot of interesting things here. Next thing is a sandbox. As I say, sandbox prevents application of getting full access to a file system. It prevents of usage of the critical system APIs. And if you want to use these APIs, you basically need to patch the sandbox. There's a few ways of doing it in iOS. There is a function called sbevaluate, which triggers in the most of sandbox hooks. So basically, it's grant access for an action. The action could be different, like a file access, like a export kernel task, or so. So we can patch this sbevaluate always return true. So everything is granted for any action. Well, it's doable, but not a good idea, because it will lead that any application downloaded from App Store or any third-party application now will have full access to a file system, which is not good, which is a really big privacy leak. So better to just hook sbevaluate and check for interesting action and grant access only for interesting action we need. Or as an alternative way, patch sandbox MAC policies directly. This is how it looks like. Again, sandbox kernel extension have a pointer to MAC policy configuration, which is a structure, which is one of the field have MAC policy operations pointer. MAC policy operations, basically a pointer to a sandbox hooks. So if you look for seatbelt sandbox policy string in a sandbox extension, we'll find a reference to it, and a few bytes up, we'll see a a few bytes bottom, sorry, we will see a pointer to MAC policy operations. And the MAC policy operation will look like this. So it's like an array which contains pointers to hooks. So we can null out everything or null out just interesting hooks. So here is an incomplete list of sandbox hooks. For example, as we see, bind got checked, stat got checked, mount got checked, rename, and so on. So we can disable only like partial hooks. The next thing is a MAC mount, and my friend Vlad will talk more about that.
Okay, let's discuss MAC mount problem. So if you need to change iOS configuration, install persistent, and many other examples, you have to remount root partition, which is read-only access by default without jailbreak. But you can just call MAC mount syscall because there are many checks inside it. So we have two general ways how we can bypass this problem. First, we can just patch these checks. First, you can call mount command function. So actually MAC mount call MAC mount after all its checks. So if you look at MAC mount syscall, you will see code that prevents mounting partitions with other flags other than read only. So if we patch this check, we can call mount function from user mode. But that's not all, because there are additional checks inside lightweight volume manager kernel extension. Method called map for IO. So root partition is still write-only access. Okay, first of all, we need to patch map for IO check, and from iOS 9.3.2 first beta, first appeared new function called pay icon has kernel configuration. So you need to bypass this check too. Here you can see two checks inside map.io function. First call pay icon has kernel configuration. You can patch it in different ways. For example, you can patch just GOT inside white volume manager, and you can just force return 1 in the pay icon has kernel configuration function itself. And second check is write protected flag of partition class. So you can patch this byte directly, or you can just patch this check. But for that you need bypass kernel patch protection. It's next big topic, and Alex will explain you.
Hello everyone. So as you've noticed, we need to make quite a few patches. And kernel patch protection is a thing preventing us from doing that. So let's take a look how it works and how to bypass it. So kernel patch protections randomly checks for kernel pages, translation tables, and some system registers. It's also executing on exception level 3, so we can't really disable it. But we can apply patches and remove it between checks. But is there any other way? Yes, it is. So let's dive deep into the iOS and find out how it works. So it all starts with interrupt. The interrupt handler sets the CP ACR access trap on EL1, and then it sets the SMID 14-point register instruction trap for EL0. Then it disables interrupts to prevent going to this handler again. Then on exception level 0, when SMID or 14-point instruction is executed, the trap is triggered, where the kernel is emulating a floating point instruction or SMID instruction, and then it's actually trying to remove the SMID trap by changing CP ACR register. This triggers another trap in exception level 3, And there, the kernel checks all the hashes for the translation table, pages, and registers. Then it removes CPACR trap, and then it removes SMID floating point trap, and finally it skips, jumps over the instruction, the CPACR instruction in AL1. Then it enables interrupts again, so the next time it will start it from scratch. So as you can see, we can't really stop kernel patch protection from checking original pages. But if you think about for a moment, we can't really stop kernel patch protection from changing original pages. So let's say we're gonna use pages which are not so original. Take a look at the translation table. We have several levels and the pages. Now let's copy the level 1 table. So after the copy, we have descriptors pointing to the original level 2 table. Now let's create another copy of the level 2 table and change descriptor in the level 1 table to actually point to this new allocated one. So that's what we have. So now repeat the same trick for the level 3 table, like that. So now we have level 3 copy with all the descriptors pointing to the original pages in the kernel, for the kernel. So now let's allocate some pages in the kernel which we really want to patch, and then update descriptors in the level 3, like that. So essentially we have two tables. One is a original table, and another one is the partial copy of translation table with our pages patched. So it all looks complicated, and you actually need to consider a lot of various things like granules, then initial levels, and addressing region. In Fried Apple, we love tools, and in order to manipulate table translation easily, we actually implemented the barbecue framework. So this framework helps us to walk through the descriptors on the various levels and modify it if necessary. Then it's a C++ template-based lightweight framework with a C wrapper. So it can relocate tables for you in just literally a couple of lines. And also, the big bonus, it can check some of your dump mistakes on the compile time. So, but let's get back to the bypass technique. So, as I mentioned above, the CPACR access triggers kernel patch protection checks. But let's replace it with branch with link instruction to some CPACR trampoline, which we place somewhere in the kernel, like replacing the knobs. And this trampoline actually jumps to the shell code. Let's call it CPACR hook. In this CPACR hook, we are restoring the original values of TTBR. Then we actually trigger KPP by accessing CPACR. And then when everything is done and all checks are performed, we're restoring our fake values of TTBR. But is that it? Well, not really, because our devices like to sleep. And when they wake, the kernel actually restores all the CPU state. And during this restore process, there's a function called TTBR restore, and our fake TTBRs are actually overwritten with original ones. So, like, the address of this TTBR restore is calculated based on a virtual base plus some offset. We can't change this offset, but what we can do, we can replace a virtual base. So, if we hack it, like you can see this formula on the right, and then we are falling into the TTBR restore hook function. In this TTBR restore function, which is a shellcode obviously, we can restore the virtual base, then we need to restore the vbar register, then we need to set our fake TTBR registers, and then call the original TTBR restore, skipping just two first instructions. Now KPP is finally bypassed. But this trick unfortunately closed in iOS 10.2, but there's another one when you can hook the deep sleep and idle sleep handlers as well, but it's a lot more involved, unfortunately. So after that, you may like to have all the same patches in the kernels applied when your device rebooted. In order to do that, this is called persistence, and in order to do that, you need to find service that spawns on boot. Then you need to make sure that it's actually running en root. And then you need to find some user land code sign bug, and then using a symlink to a system service, you can exec this binary to bypass code sign. So in our jailbreak, we're using JavaScript core interpreter, which is signed by Apple, and what's good about it, it can execute code in RVX segment. So we are copying in at a system service to be spawned on boot. So that's what it looks like. So we're replacing RT by DD service by GSC, and then we're creating early boot file, which is essentially a JavaScript exploit with a payload. So when the system starts, it executes RT by DD minus early boot, which essentially is JavaScript exploit. So it looks easy, but the payload needs to be crafted specially because you don't have much load or anything like that in there. So our payload doesn't actually have import. And we need to find in the memory DLSIM, then we need to update address, then we need to resolve all the import, and then finally, when using some code sign bypass trick, we need to run our jailbreak binary to restore all the patches in the kernel. So after that, it's nice actually to have some SSH access to your device. So you can do this in two different ways. You can install CDR or copy drop beer. Then on a desktop computer, you're just using TCP relay, which creates a tunnel to your device. And then you use regular SSH with a password Alpine to access your device. But it's not really needed for security researchers, but for most people, jailbreaks means CDR. And to install CDR, you need to copy tar somewhere. Then you need to use tar to extract CDR bootstrap to put all the files to the right places. And then if you don't want CDR to symlink all the system files to bigger partition, because system partition is pretty small, we need to create a CDR no stash file which prevents CDR from doing this. Then you need to use UI cache to flash UI and finally get a CDR icon on a screen. As we know, Apple is working hard on security enhancements. And in iOS 10, they introduced quite a few. So the first one is like next new heap layout, but it's very well described and by various security researchers in many write-ups and articles. So I would like to concentrate on Amphi, Sandbox, and kernel patch protection. So speaking about Amphi, they introduced new function misvalidate signature and copy info, which is actually using CD hash and can be hooked or replaced with just CDF equal to bypass code sign easily. Then they fixed the race condition invalidate code directory hash and daemon, so you can't replace file after signature is checked. But policy patches still work. So as for Sandbox, they introduced new profiles, new operations, and new hooks. So if you need to get some functions to work, so you need to patch some of these new hooks and policies as we described above. But most important thing is KPP enhancements. So they introduced new kernel cache layout when the code and the data cons they stitch together. So and God segments are actually protected, so no more like easy hooks. And interesting thing, they actually introduced some hardware mitigations on iOS 7, iOS 7 Plus. So let's talk about these hardware mitigations. So they started to use a thing called AMCC, which we believe stands for Apple Memory Control Chip or Access Memory Control Chip, which watches memory region for any access, and it prevents writing inside the region or execute code outside the region. Let's take a look how it's initialized. So on the start, kernel performs several stages to initialize itself. And one of these stages is actually AMCC initialization. So they're actually taking the pre-link virtual address and then last virtual address of the segment, and then converting them to physical address. Then they're using these values to set AMCC registers. Then they're stashing these values as well in the global variables. As we know, after device wakes, we need to restore the CPU state. So what happens in a low-level reset handler, they're actually restoring all the AMCC registers from the stash ones. So now we have kernel patch protection working back again. So what is the future of jailbreaks? It's not that shiny because iOS is getting more and more secure and more stuff has moved to the hardware side. Also exploits will be more valuable and unlikely appear on the public, but there will be still bugs and nice write-ups, and some researchers will share information for free. So there is still hope. Now let's go to the demo, and I would like to know that if we have a different exploit chains for our jailbreaks, the actual structure and the flow is almost identical. So let's start with 4.1 jailbreak, and I would like to ask Max to help me with that.
Thank you, Alex. Yeah, so we made a various jailbreaks, and we start from them in 8.4.1 jailbreak. So the general idea that we made the same structure in all jailbreaks for iOS 8, iOS 9, iOS 10, and we're trying to connect. we're trying to connect to a device using the known port on a device. Using a local host, TCP relay and local host on a known address. So as we see, the connection got refused. So we're running iDevice syslog to show, like, step by step how the exploit works. So we're starting from exploiting a kernel, finding the patches, writing patches to a kernel, and finally spawning SSH. So now if you're trying to connect to a device, the connection will succeed. And to prove that there is, like, basically the same kernel version that we just found it, we'll compare the XNU versions here. So as we see, the XNU version is the same.
Yeah, the next jailbreak is iOS 9 jailbreak, and this one differs from other ones because it has a persistence in it.
Yeah, again, the same structure. So we're trying to connect the device for a known port, connection got refused. Now we filter everything in iDevice syslog to show only our exploit and connection and connected and disconnected events. So exploit got started, kernel dump it, patches applied, we install the persistent binary, which means that the next time device will be booted, it will run our exploit once again. Now I try to connect to a device with the same address, and it succeeds. We got a shell. We use uname-a to prove that XNU version is the same we just exploited. Yeah. So the next thing, I'm going to reboot a device and prove that exploit will be run once again when the system will be booted. It may take some time as kernel loads all the extensions, it loads all the system services, so it's usually based on a device type. It's pretty fast on 6S and 7.
Unfortunately, we can't have logs from our payload, so like we're waiting. Yeah.
As we see here, after the device got connected, exploit starts again, but now we are not installing the persistent binary, and it's found in the SSH. So we're trying to connect the device once again using the same address. We got a shell. We use uname-a. Again, we comparing the XNU versions in a log and device we just found it. They're the same.
The next demo is iOS 10, and please note that it has exactly the same flow. So, but the exploit chain is actually different.
Yeah, we just want to show with all the demos that the structure is the same, but the only one thing that's different is actually the exploitation. So again, trying to connect the device, connection got refused, running kernel exploit, which will find and apply all the patches and spawn in SSH. Now if we try to connect to a device with the same address, we got the shell spawned. uname-a, and the version is the same.
The next is tvOS, which is a different device, but apparently the same structure.
Yeah,
Take a look.
we get a Apple TV 4, and we say, okay, so it's pretty similar than the iOS. Why not exploit the TV? So this is how it looks like. Again, we're trying to SSH to a TV. It's not working. We take the similar exploit as we use it for iOS 10 with some various modification to a kernel patch protector. Click in a base, dump in a kernel, find in a patches, spawn in SSH. Now we try to SSH to a TV. So the TV that we just showed, it was Apple TV 4 running tvOS 10.1. So as you see, we got a shell spawned on a TV. And with the uname-a, we can prove that the version is the same that just found it.
Finally, watchOS, totally different device, but who would have thought same structure?
Yeah, so we got to watch and ask, why not try to pound the watch? So the exploitation is a little bit different as we cannot connect directly to a watch. So we need to set up a Bluetooth proxy over the watch and the iOS device and proxy between the device and a Mac. It makes some time because watch is a slow device.
And we have to use Xcode, unfortunately.
Yeah, unfortunately, iDevices log cannot read the watch log, so that's why we need to use Xcode output to show how the exploit works.
It will take some time because watch is a pretty slow device, unfortunately. But let's be patient.
Okay, it's running. It's just a couple of seconds. Yeah,
Yep.
we got exploit starting on a watch. It will be more slowly, like kernel dump sometimes take like for 20 seconds for us. Yeah, now it's a bit faster. Yeah, we got SSH spawned. So the next step, what we need to do, we need to set up the Bluetooth proxy over the device and a port 22 on a watch. I use a script that I written to bind port 533 to a watch port 22. And I just SSH to this known port on a device. As we see, the shell got spawned on a watch. You get your name, we got a root XNU version on a watch 1.2, and it's exactly the same we just showed in Xcode. So the watch.js is spawned.
Okay, let's sum up this talk. So jailbreak is totally doable with just public bugs and public write-ups. And you can use patches and description for KPP bypass from this talk to jailbreak all devices and XNU.
Yeah, so check the XNU. XNU is a great source of bugs and possible 0 days, and as well as doing a really great help to understand how the kernel works. So we spend a lot of time inspecting the XNU sources. Thank you very much. We are Fried Apple team. If you have questions, follow us on Twitter, and I think we still have a time for questions.